so, this was sent an email, but I want to reemphasize the problem sessions now removed to the time slot on Friday, 1 o'clock to 2 o'clock, and that's next door in 1160. All right. Right. So the recordings of the lectures are being posted, and you can look at them as you like. I want to talk about this and how flexible people are in some of these, because there's no time for that looks reasonable for TA office hours. There are some like better than others. So like, what are you guys doing at 9 o'clock?
Wait, why am I says I'm unavailable?
Yeah, exactly.
When am I available?
So, okay, so I wasn't clear. Like, I know these people that are free then. What are they doing? I know you people. So, yeah.
For example, we have journal review meeting at that time.
Okay, some of you do, but not, I know some of you, I see you in your office. You're just hanging out. So, anyway, let's fill this out, look at it again, make sure of this, and then I'm going to find some times, okay? So, try to be flexible, and I mean, if you have a commitment, you have a commitment. If you don't have a commitment, you're available, okay? All right. Enough of that. Yes, I need it. Turn it on. All right. Very good.
Oh boy,
All right, so let's just quickly remind ourselves where we were when we were discussing last time. So we're talking about what in modern jargon is what people call CV, or continuous variable quantum optics, okay? Which is to say, we'll be studying the properties of the quantum field, not with respect to the discrete variable, which is the number of photons and the photon statistics, but in terms of the continuous variables which are related to the quadratures. It's kind of like, are we talking about the particles or are we talking about the waves? There's a quantum wave-like aspect to the field and there's a quantum particle-like aspect of the field, and both of those things are important in understanding the quantum properties of the field. We studied last semester mostly thinking about this in terms of discrete variables and the Glauber theory, etc. Okay, so so there's some algebra, boson, as what's sometimes called boson algebra. I mean, yes, the photons are bosons and the boson, but really this is just wave mechanics. Okay, I mean, it's just the properties of position and momentum and wave functions and the like. Okay, so just to quickly remind again, so to be able to deal with the mathematics of this, there's just some tricks of the trade. So we talked about different kinds of transformations in phase space. So we have the operator that rotates the phasor in phase space, defined as such. Okay, it's generated by the number operator. So the number and phasor conjugate variables, right? So momentum generates translations in momentum. Momentum generates translations with position. Number generates a translation in phase. There's no phase operator, but yeah, c'est la vie. All right. So in any event, this is the transformation. We have a unitary transformation on the operator, which the annihilation operator picks up this phase under the rotation operator, and the x and p coordinates rotate in phase space. It's a passive rotation on the basis, okay? But the rotation on the phasor is the other direction. It goes clockwise, right? So that's the difference between a passive rotation and an active rotation of the vector. that you think about that. So the action of the rotation operator on the coherent state is it takes the coherent state to the coherent state that is rotated clockwise, okay? Either the minus I phi or theta in this case. Okay, so that's the phase-space rotation. We'll use that a lot. And another very important transformation we have in phase space is the phase space displacement, okay? So this is a very important operator, and we'll see it a lot. It has this form. Memorize it. You just got to know this. This phase-space displacement operator, written in terms of the real and imaginary parts, the x and p quadratures or coordinates, has this form. It symmetrically transforms in x and p. It doesn't do first translation in x and then p or vice versa. It's symmetric, okay? The term symmetric is going to become important later. So the action of the displacement, the unitary operator displaces the annihilation operator as expected. It displaces it by the amount in phase space alpha. And so what that does is it displaces x by the real part and p by the imaginary part, okay? So it does a translation in both x and p. And moreover, the set of displacements is a group, okay? Formally speaking, it's a set of operators that have a composition law. So if I have two displacements, one by displacement by complex amplitude beta and one by, and I do them in succession, I just, first displacing alpha and displacing beta, but I also have this phase, okay? That phase is arising because x and p don't commute, okay? It also means if I were to do a displacement and bring it back to where it started, I would pick up an overall phase. That's sometimes known as a geometrical phase because it depends on the geometry. And it was initially, this was an important idea that people had, in making, if people are familiar with the Mulmer-Sorensen gate for ion trap quantum physics to name people here, that's where it comes from. It comes from that geometric phase. Okay. All right. So I just want to mention one kind of aside in all of this. We said what we see for if we have these are the unitary operators. The unitary operators are generated by Hamiltonians, right? You exponentiate the Hamiltonian, that gives you the unitary transformation. So these two sets of operators, the rotations and the displacements, are generated by things that are linear in A and A dagger or X and P, and and also include the number operator, A dagger A, okay? And what we see here is that if we have Hamiltonians of this form, then what they do is they don't change the photon statistics, right? They take a coherent state to another coherent state. Moreover, if I had a statistical mixture of coherent states, a classical statistical mixture of coherent states, which is what we're defining to be classical light, then this kind of transformation also doesn't change the photon statistics, because it's just taking the coherent states to other coherent states, okay? So what that means is if I start with some kind of light that I would call classical light, and I transformed it this way, it would still be classical light. I can't make non-classical light if all I have are displacements and rotations. This is a general, or of a more, if I had a multivode, this transformations that we're talking about at the moment, we're restricting our attention right here to a single mode of the quantum field. If we had multiple modes, we could generalize this to say, you know, all of the generated by the creation annihilation operator for any mode, and something that might look like this. If this labels the mode, I and J. So these are displacements in the modes, and then what this does is it annihilates a photon in one mode and creates it in some mode. If I equals J, well, that's the number operator in that mode. If not, it's just what we would call a scattering process. It scatters, it takes the photon out of one mode and puts it into another. We studied that last semester, for example, in a beam splitter. That's an example of a scattering process. And this is what we call linear optics. And we'll talk about this more, if I have a linear optical transformation, that's all I got. And linear optics, thus, can't turn something which we would call classical light into non-classical light. We need nonlinear optics to do that, and we'll talk about that some more. Yeah?
So linear optics is when our Hamiltonian is always an A dagger A.
Or just something proportional to A or A dagger.
Okay.
So it can have an A, so this is displacements, and this is rotations or scattering.
So I and J can be different.
They can be different, yeah. And then it would be a scattering event.
Which is still linear optics.
That's still linear optics. So if I have a beam splitter or a lens, I take a ray and move into another one, that's linear optics. So linear optics kind of acts photon by photon. It doesn't, that's what makes it linear. There's nothing that has to do with the correlations between photons. And it's the correlations between them that is where we get the non-classicality. Good. All right. So continuing then. Right. So let's talk about other properties of non-classical light. So, again, we've defined classical light, and for the moment, I'll just restrict my attention to a single mode, because we can easily generalize this to a multi-mode case, as a statistical mixture of coherent states, where this is a semi-positive definite probability distribution, okay? So what we saw, again, what we've seen, some properties of this non-classical light are, for example, if I look at the fluctuation in the number of photons in the mode, right? That's the expected value of n squared minus expected value of n squared, then that's equal to that, right? It's the fluctuation in photon number for a coherent state, and then I have to take the statistical mixture to get the overall fluctuations. The fluctuations in the coherent state here are equal to the number, right? Which is, so that's the mean, that's the fluctuation in the coherent state for that, right? That's equal to the mean photon number for that coherent state. But if I have a statistical mixture, I can only make the fluctuations worse. I can't make the fluctuations reduced by that, which is to say this is always then greater than or equal to the mean photon number, which is, as we said, for classical light, that means we have super Poissonian statistics. We always have fluctuations bet more than number counting. And that we can think about as coming from the classical intensity fluctuations. Okay? But we can also think about other aspects of life. We think about the continuous variable. I can think about a quadrature, like x. And I can ask, what are the fluctuations in the x quadrature if I have classical light? Okay? So that's, again, the mean of x squared minus the mean of x squared, which is equal to that. Okay, everyone with me? So this is the fluctuations in the quadrant for a coherent state. How big is that in a coherent state? So we've gone in dimensionless coordinates here. H bar effectively is 1 because we've gotten rid of all the units. But so in these units, it's a half, right? Because it's the same, and we've done this calculation before, I'm not going to do it again. It's what the fluctuations in the quadrature of a coherent state are the same as the fluctuations in the ground state. And we remember from a harmonic oscillator that those fluctuations for our H are related to, the characteristic length over 2. So this is equal to a half.
Can we get it from the fact that it's a minimum also?
Yeah, but exactly what that number is, we have to remember. But yes, the answer is a half. That's the variance. The RMS is 1 over square root of 2. The product of delta x and delta p, thus, is a half, which is the minimum uncertainty product. And E, right? Okay, so this is also true for p. For a coherent state. Okay? In fact, for any quadrature, this would be true, no matter what quadrature I take. But okay, so if it's a coherent state. But if I have a statistical mixture of coherent states, by the same argument, and we can just do it, this can only make the fluctuations worse. Can't make it reduce because we have more statistical uncertainty. So this is, what this says is that if I have classical light, this is always greater than equal to a half. It's only equal to a half if I have a coherent state. And if I have a statistical mixture, which is, I can only make those fluctuations worse, okay? So the minimum I can have is the vacuum level. That's the lowest, if I have classical light, I can never get it below vacuum noise, okay? So if the fluctuations in some quadrature, doesn't matter, any quadrature, could be x or p or anything in between in this rotating direction, it doesn't matter what direction I look in. If this is less than a half, we say that we have a squeeze state. Of the light. And that we can't get by starting with classical light. We need some nonlinear optics to make squeeze light. We'll talk more about that next week. But if we have it, that's a signature of something which is non-classical. Yeah?
Is it then still the case that the variance in P is equal to the variance in X?
No, it is not. Because then I would violate the uncertainty principle. So it's always the case that delta x, delta p, by the uncertainty principle, is always greater than or equal to a half. So if this is less than a half, then necessarily the other quadrature will be bigger than half. We can't have them both reduced. Yeah.
If the alpha delta x squared alpha is a half, then isn't that always equal to a half because you pull it out and then integrate over the probability distribution? And then that's one.
That's an interesting point. Yeah, so my argument isn't quite as simple as I wanted to make it. I really have to let me think about that, Leroy. You make an excellent point. So where did I go wrong here? This is correct, okay? So it's because the square is outside. What I just did was garbage. This is correct.
Okay.
But thus, I can see that my fluctuation will always be more, yeah. But you're right, what I wrote down was too fast, too dirty.
So that top line that you have circled there is also wrong, or is that one okay?
Yeah, it's also wrong for the same reason, yeah, yeah. But this is also true. Because of the way this is. I can never make it less than what it was for a pure state if I have a statistical mixture of those states. That will only make it worse. But the mathematical argument is not quite right. Thank you. Keep me honest. Pull that wool over your eyes. All right. Very good. Okay, so let me just remind myself what I wanted to say here. Oh yeah, okay. So let's try to understand a little bit, sort of in a more physical picture, what this is saying about the need. What do we mean by these fluctuations? So let's say I have a coherent state. In phase space, I have this state, which is rotating around with the phase e to the minus I omega t, right? Let me drive a little bit more. Let's just say the mean of this thing is going around. That's supposed to be a circle. Let's try it again. And so this uncertainty bubble is the same uncertainty bubble. As we said, the coherent state just rotates around. The fluctuations around that are exactly the same at any point because it's a coherent state at any point. And a coherent state has the same fluctuations in all quadratures, okay? So if I were to do a measurement of x as a function of t, well, the coherent state is not an eigenstate of the number operator. So there are fluctuations in the number. Those fluctuations are equal to a half. Which means that when I measure x at any time, I don't get a deterministic answer. On average, the x coordinate just undergoes harmonic motion. If I look at the projection of x, of this vector on the x-axis, a function of time, is undergoing. So let's say at time t equals 0, it was here. So x is at its maximum, and it's a cosinusoidal function, right? So this is pi over 2, pi, let's say this is omega t, and this is 2 pi, okay? But when I measure x, I don't get a definite value. So at any time I have some probability distribution, we can remind ourselves what that probability is. Of course, it's a probability density because this is a continuous variable. But I can just kind of sketch it, you know, maybe I get this value, then I get that value, and 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 then I get that value. And I get some, this is my attempt at fluctuations around that. It's a noisy thing, okay? But the statistics are the same in the sense that the sort of, what I tried to draw in my best I could is the fact that if I were to think about the 1 sigma variance for RMS around this thing, it's the same. So this delta x is the same at all times, which is the same, the projection of this, what's supposed to be a circle, at every time is the same fluctuations. You know, I'm gonna get random values, but the way those x fluctuates is the same at every point in time. And that's the characteristic of the coherent state, okay? But now let's suppose I have a squeeze state, a state that has fluctuations that are less than this width, which is, you know, 1 over square root of 2, along some quadrature, okay? So I'm gonna say, for example, what I'm gonna write down here is an example of what we call a phase squeeze state. So let's say, what do I mean? I'll explain why I'm calling this a phase squeeze state in a moment. But let's say at time t equals 0, I have a state which has the same mean value, but is squeezed, okay? And it's going to be squeezed like this. So that at time t equals 0, so this is what I would have had if it were a coherent state. And this is this ellipse is representing the fact that the fluctuations, in this case, in delta p, are less than 1 over root 2, okay? Which would mean the other guys are bigger.
Why is it 1 over root 2 not the half?
The half is for the squared,
Oh, I see. Okay.
okay? So the variance is a half, the RMS is the width itself, okay? Yes, sir.
Just to confirm, the squeeze state and our unsqueezed state should have the same center?
They should. I mean, in this case, I'm assuming that I'm considering a coherent state that has the same amplitude. I mean, the squeeze state has the same mean of x and p, but different fluctuations. Now, as we've discussed, irrespective of the fluctuations, the mean value follows the classical trajectory. That's just because the rotation operator does this to a or x and p, and they rotate by the free evolution. So this thing will rotate again around as a circle in phase space. So, you know, at some later time, it will look like this. And then it will look like that. 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 And then it will look like that, etc. Okay? And this is rotating around with that phase. But unlike this picture, when I have this kind of state, the fluctuations along x are different at different times, okay? Here, those fluctuations were huge in x. But at this time, they're very little. They have less fluctuations along x than the vacuum level. When I'm at, you know, a half a period, I'm back to having the same that I had initially, and then they're small, and then they're big. So, okay, I'm gonna try to attempt to draw this. I'm not very good, but I'll do my best. So now I want to draw what I would expect to see. What's a particular example of a measurement record that I could see here? As before, the mean of the measurement outcomes, the expected value of the measurement outcome, is the same for this state as this, because the mean value undergoes the same trajectory. So I'll have the same cosinusoidal function as before. The mean expected value of x as a function of t, or omega t, is the same in this, but the fluctuations will be different. And moreover, what we see is at time equals 0, these fluctuations, let's just make an error bar, they look like this. Whereas, so this is at time equals 0, but at time a quarter of a period, or pi over 4, I have smaller fluctuations than I did compared to here. Okay? And then when I'm at a half period again I have big, and then I have small, and then I have big. So if I were to try to look at this the RMS of this thing, it would look like that, which has skinnier fluctuations over here and bigger fluctuations here. So the measurement record might look like this. So unlike this, where the fluctuations were the same at all times, here they're different. And most importantly, why this is called a phase squeeze state is that I can see with more certainty when this thing crosses 0 with the phase squeeze state than with this, because my uncertainty when x is 0 is less than it was for the coherent state. So I can measure the phase of oscillation better, okay? This is what's called a phase squeeze state. Yes, Tristan?
Just to verify my understanding of
Yeah.
this phase space. When we draw these circles or these ellipses or whatever shape we draw,
Yeah.
that's a representation of how much uncertainty you have in that area, but it's not like we're actually saying you can only get these
Correct.
values.
No, this is a ball and stick model of this, meaning that this is just, I'm just thinking about this as we will remind ourselves, the probability distribution of different values of alpha is a Gaussian. So this represents just the contour of the 1 sigma. I have a continuous distribution of possible alpha with a probability distribution that's peaked here and falls off, and the variance of that distribution is what I'm drawing here. So this dashed line that I'm drawing here, the fact this can go above or below that dashed line, but it's showing me what the RMS is. So that's, yeah. Yes, Benny?
Yeah, so when I see, these two signals and
Yeah.
one where the sigma is being kind of modulated, it's sort of, to me it indicates this might be more complex than Fourier space, right? Because this is another wave that's happening.
That's right. I think that's fair. There is another frequency in the problem and it's related to the, as we will discuss more next week, and as you're looking at in your first problem, the homework said, it's related to parametric oscillation. So we're driving the system at a second frequency. There is another frequency in the problem.
So the squeezing necessarily implies another kind of oscillation.
It does.
Okay.
Absolutely. Yeah.
So because we don't have a phase operator, we can't measure the phase directly, so you're saying we measure X over a certain time and then,
Yeah, I mean, there's many ways to ask about what we mean by phase. If I'm thinking about, and I can measure the phase by asking at what point does the oscillation go through zero,
yeah,
right? That is a measure of phase. As we discussed a little bit last semester, there are other ways that we think about phase as in terms of a canonical phase measurement, meaning a measurement whose outcomes are described by some POVM that has the properties that we want to think about as conjugate to number. The fact that there's not a Hermitian operator whose eigenvectors correspond to those measurement outcomes is irrelevant. We don't need no stinking Hermitian operators to talk about measurements. All we need is a POVM. The Hermitian operators are just a subset of them. So, but there are, I think back to your question, it's really a question of operationally, what do we mean by phase? And in an interferometer, I have a definite definition of a phase, and then the phase squeeze state is the way I would measure that phase, exactly the phase.
and just by looking at the uncertainty over time.
That's right. Okay, let's just so now I'm going to have what I call an amplitude squeeze state. So now I'm going to just have the opposite case where I'm going to have, at the initial time, I'm going to have the X uncertainty be the small guy and the P uncertainty, right? So this is my coherent state and this is my amplitude squeeze state, okay? And again, this thing goes around in a circle and, you know, it looks like this at different times. Okay, so what's different about this guy now, as I look at this, again, as before, we have, you know, the cosinusoidal mean, but at the initial time, I have the small uncertainty, and I have the big uncertainty when it crosses zero. When X is zero, the uncertainty in X is big, okay? And vice versa. This guy is small, and this guy is big, and this guy is small. So if I look at this situation, I have this kind of uncertainty that looks, the uncertainty ellipse now looks more like that. Which is to say, I can make the amplitude is very squeezed, but the phase, or where it crosses zero, okay? So it's a different kind where I know what the amplitude is, but then I don't know what the phase is very well. Okay, that's. I can also talk about what we call as vacuum squeeze state. Or squeeze vacuum. So if I have the vacuum state, again, I can, if I had to measure X as a function of time, and we'll talk about how we do that next week. if I can make that measurement on the vacuum, it's not an eigenstate of x or p, and so I'm not going to get a definite answer. The fluctuations will be the same at all times, that is to say, the variance in the measurement outcome, but I'll see what we call shot noise. It's not supposed to be periodic, okay? It's supposed to have just noise, my best attempt at that, but it's the same amount of noise at any time. On the other hand, if I had something that looked like this, where this is the vacuum level, so that I had, then this ellipse rotates, well, it rotates this way. And what I'm going to see in that case, if I were to measure x, is at the initial time, it's small, and then it gets big, and then it gets small, and then it gets big, and then it gets small. And my fluctuations, well, they're supposed to be all orange, would be less over here, and then get a lot, and then get very quiet, and then get loud again, and then get quiet, etc. Okay? And this period here, this would be 0, pi over 2, pi over 2, 3 pi over 2, 2 pi. The period of this oscillation is twice the period of omega. Can you see that in terms of this ellipse? So at a quarter period, I get the most. At the half a period, I'm back to where I was in terms of. So this goes back to Ben's question that we have this double. This has a frequency of 2 omega. Okay, that's important.
So when people say shot noise, they mean the quantum fluctuation.
That's right. So we'll talk more about that. When we talk about shot noise, what it means is noise from shot to shot. So you take a measurement and each shot you get, so when we count photons in a given time interval, that's a shot. We take one shot, we get some number of photons. The next shot, we're going to get a different number of photons. Now, where does that shot noise come from? Well, fundamentally it comes from quantum fluctuations. But also, not just in counting number of photons, but in terms of these quadrature measurements.
So in the device, we would want to sample at 2 omega, at precisely.
Yeah, I mean, well, yeah. So we'd have to think about how we make use of this measurement in the right, how things have to be, the local oscillator has to be in the right phase relation to the oscillation of the state in order to see those produced noise. Cool. All right. Yes.
If we look at like a tilted ellipse,
Yeah.
like the 45-degree one,
Yeah.
the picture of the ellipse kind of makes me think like the range of x is correlated with what p value you get. Is that true, or is that just the ellipse picture not being honest?
Well, so no, they are correlated.
Okay.
They are correlated in a certain sense. The range of p and the range of x's are in these relations. So the range of expected p's are related to the range of expected x's just because I have this ellipse. Yeah. Yeah.
Why do we distinguish between amplitude squeeze and phase squeeze state? Because if I measure P instead of X, they should switch, right?
Can you repeat the question? I didn't understand what you're asking.
This is an amplitude squeeze state if I measure X, right?
Yes.
But if I measure P, it will become a phase squeeze.
That's right, but the question here is, what is the squeezing relative to the direction of the mean? Okay. So if I measured P, the whole thing would be phase shifted by pi over 2, but it would still be the case So when the P goes through zero would be the opposite, you'd have more fluctuations. But what we're measuring in this case, I mean, the issue here is what is the mean value compared to, is the direction of the squeezing more or less relative to the direction of the amplitude? If I measured P, the whole function would be shifted, right? But when P goes through its maximum value, in that case, well, that would then be squeezed. So we would still see the same features when, you know, in this case, P would have the biggest fluctuations when it's in this case, right, so P, no.
I think that's X maximum, but P fluctuation minimum there.
This is where P is maximum,
Yeah, but fluctuation.
but the fluctuations would be minimum P. So it would be amplitude squeeze in P. It would just phase shift this whole thing by pi over 2. It's when X or P goes through 0, the question is, what are those fluctuations? All right. So let's talk about, we need to move a little bit faster here. I want to talk about the formal description now. Okay. So let me define what I'm called the squeezing operator. S of R is defined as the exponential R A squared minus R A dagger squared. Sure, I got the sign of that right. I think I did. Yep. Where R is a real number. Okay. Is this a unitary operator? How would you know? So the thing in the exponent has to be anti-unitary, or I times a Hermitian. When I take the dagger of this, do I get minus that?
Yes.
Yes. This is a unitary operator.
You mean anti-Hermitian rather than anti-unitary?
That's what I meant. Anti-Hermitian. Yes. Okay, so it's a unitary operator. And we can think about a unitary transformation on this. So let's calculate that. Let's see how this transforms the annihilation operator. How do we do that? How do we find that? We use BCH, okay? So let's just remind ourselves that Baker-Campbell-Hausdorff theorem, which tells me that e to the minus b, it's about similarity transformations, of which a unitary transformation is one, that this is equal to a plus the commutator of b with a plus a half the second commutator, b with the commutator plus dot 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 1 over n factorial n times doing that. Right? That's the BCH theorem. And that's how you calculate these things. So in this case, B is equal, so S dagger, let me make sure I get this right. It's the other way around. That's correct. So, in this case, this operator B, if I take the dagger of this, then this is equal to minus. And that commutator, thus, of this with the annihilation operator is going to be equal to R over 2, the commutator of A dagger squared with A, which is equal to minus R A dagger. Because the commutator of A dagger with A is minus 1. The commutator of A with A dagger is plus 1. So, I'm not going to go through all the algebra, but importantly, this multiple commutator algebra closes because every time I commute B this a second time, I'm going to get now A dagger commutes with that, which will be something proportional to A. And then I'm back again, and goes over and over again. I never get more powers of A or A dagger. I only have things that are linear in A and A dagger when I do these multiple commutators. And so what one finds when one does that is that this is the sum over the even integers and then I have minus the sum over the odd integers. What is this function? Now, if these were all the ends, this would be exponential, right? But if I only have the even one ends, it's a hyperbolic cosine, and which is the e to the r times plus e to the minus r over 2. And this is the hyperbolic sine, which is e to the r minus e to the minus r over 2. Okay? So this is cosh r a minus sinh r a dagger. Okay. For simplicity, I'm going to call this script e for many of these calculations script e c and script e s. Okay. Yes.
Is R or lowercase r just like the magnitude of squeezing?
It is. We'll get to that in a moment.
Okay.
See how that goes. Right now, we're just doing some math, and then we'll see what it means. And similarly, thus, right? This, by the way, is known as a Bogel-Lyubov transformation. Bogel-Lyubov first wrote this down thinking about superfluid helium and elementary excitations in Bose gas. But in any event, what we see is that the Bogel-Lyubov transformation is a kind of rotation by a complex angle of A and A dagger. It kind of rotates A into A dagger by a complex angle. It's intimately related to a Lorentz transformation. If you remember something about Lorentz transformations, they kind of have a similar form. Okay, and the group theory of this is intimately related to that. But that's kind of neither here nor there. It's just a little aside. Okay, so let's ask now, how does this squeezing transformation, what is the unitary transformation on X? Okay, so that's equal to the transformation on A plus the transformation on A dagger. Because X is A plus A dagger over root 2. Okay, and so when I do that with a little bit of algebra, remembering that cosh is e to the plus r plus e to the minus r over 2, and sinh is e to the plus r minus e to the minus r over 2. Okay? Gotta remember that this becomes e to the minus rx. I'm not gonna do the algebra, just do it. Okay? And the squeezing transformation on P is e to the plus r. So that's interesting. So the squeezing transformation rescales x exponentially, reduces it, multiplies it by the factor e to the minus r, and simultaneously stretches or anti-squeezes P. So this squeezing transformation, as we defined it for this parameterization, this squeezes x, and what we say, instead of saying instead of saying stretching, we often say anti-squeezes. Okay? So the degree of squeezing, R is called the squeezing parameter. Okay? And moreover, we see here that if I look at the commutator of the unitarily transformed x and p, it's the same as the untransformed, as it must be, because a unitary transformation cannot change the commutation relations. All right. So what this says, thus, is if I do the squeezing transformation on any state, the products of the fluctuations have to be the same, okay? All right. So R is the squeezing parameter. It determines the amount of squeezing, and for this particular parameterization, the squeezing is along X quadrature, okay? So let's define a squeeze vacuum state like the one we sketched, squeezed along X. So I'm going to define 0 sub r as applying the squeezing operator to the vacuum. Okay? So that's a squeezed vacuum state. Let's calculate the fluctuations in the quadrature x for this squeezed vacuum state. So that's the mean of x squared minus the mean of x squared. Right? How am I going to calculate that? Well, I can calculate that by writing the squeeze state as the unitarily transformed vacuum state, and then taking the unitary transformation on the operators. So this is then equal to the expected value can think about this as a Heisenberg picture way of looking at it. You with me? So what is the mean value of x in the squeeze state? So this is equal to e to the minus rx. So what is this mean value? It's e to the minus r times the expected value of x in the vacuum, which is 0. Okay. And this then is equal to e to the minus r, or 2r, that.
Because it operates twice.
Because it's squared,
Oh, I see.
right? And this is equal to, for the vacuum, a half. So the variance in x is squeezed for a squeezed vacuum, and the variance is squeezed by minus 2r. Now, a lot of times when people say, how much squeezing do I have? They love to talk about the amount of squeezing in terms of the variance, because you get to take it to the squared power. So, 10 dB of squeezing is really 10 dB in the variance. It's really the square root of that, if you want to look at RMS. But everyone loves to talk about the amount of squeezing in the variance, because it just seems like you have more. Very good. So what is for this squeezed vacuum state, what is the fluctuations in P at this initial time? Correct. So that the product of this times this, in terms of RMS, is a half. So a squeezed state is a minimum uncertainty product. This particular pure state so the state as we've drawn it before, this is the coherent state. This guy is, this uncertainty ellipse is like this. The product of this times this is a half. It's a squeeze state because along the x quadrature and others, it has less than a half. But it's still a minimum certain product. And that is because you can never have it be smaller than that. That's the uncertainty principle. It could be bigger, but the pure state, because we've obtained it by unitary transformation, does not change the uncertainty product. Okay.
The unitary transformations never change.
That's right. Yes. All right, very good. What was next? I forgot. Oh, now there we go. Very good. All right, so let's try to understand a little bit how I can have fluctuations in, say, the x quadrature that are below the vacuum level. What's one way to physically understand this? One way to physically understand this, let's consider the case that have small squeezing. Okay, I'm going to take the squeezing parameter to be small compared to 1. So I can write, in that case, the squeezing operator as approximately equal to the identity plus the exponent. So the exponent of the squeezing operator is equal to a half r a squared minus r a dagger squared. Okay, for r small. So if I look at the squeezed vacuum state, in that case, this guy's approximately equal to, well, it's equal to this, the squeezing operator acting on the vacuum, but if I take this approximation, what I get is this is equal to the vacuum. The annihilation operator acting on the vacuum is what? Zero. It annihilates it. And a dagger, when it does that, it gives me one photon and then two photons with a square root of 2 in there. I get minus, thus 1 over square root of 2 r times the 2 photon state. Okay, I mean there's going to be plus dot 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 with 4 photons, 6 photons, etc. But to lowest order for small r, it's this. So what we see here is that the squeeze state is a coherent superposition of vacuum and 2 photon state plus small brushes that come from the 4 photons, etc. But for r small, this is the dominant effect. It's a coherent superposition, so there is some kind of quantum interference that is happening that is responsible. One way to think about is how I can interfere and get the fluctuations of the measurement below the vacuum through this interference, okay? Because we can look at this, and again, I can then ask, what is the fluctuations in x in this state, okay? Now, this term, as we just said, is 0, okay? And that's, you can see that in the superposition or in the other ways we said. So it's only this term that matters. And we can write that out as a squared plus a dagger squared plus a dagger plus a dagger a over 2. Because remember, x is a plus a dagger over root 2. We square it, we get this, okay? So this is, so now if I look at this, let's put all these things together, okay? So the terms that have, if I put this form of the squeezed vacuum for small r, and I plug it in over here with this form over here, then what do we see? Okay, there are going to be the terms that have to do with things that conserve the photon number and things that create or annihilate pairs of photons. Okay, so we can look at this, and when we plug all of this in, what we find is the following. There's the term that comes from, if I keep terms to first order, in the squeezing parameter, well, I'm going to get the I'm going to get the expected value of x squared for the vacuum. That's a half. This guy will be r squared. I'm going to ignore that. So that's the dominant term for the diagonal part. But then I have the off-diagonal terms. And the off-diagonal terms will contribute to first order because they're going to have r times this term. I'm going to have a term here with a 0 and a 2 or a 2 and a 0, which annihilates or creates 2 photons. And the answer is equal to minus a half R. So this term is coming from this, and this term is coming from the coherence. The off-diagonal elements. The interference term, they're going to contribute here. And that interference here, because of the sign choice, reduces it. Okay? For r small, this is equal to a half e minus r, the first order in r. Okay? So, the conclusion, the important conclusion of all this math is that we can think about squeezing as an interference effect. It's an interference effect that's happening because my state has a superposition of different photons, and the interference between the amplitude of having no photons and 2 photons can be destructive interference and reduce those fluctuations beyond what I had just with the vacuum itself. Yes?
So in order to actually create a squeeze state, then do we need to produce these higher photon?
We absolutely do.
Yes.
And we'll talk about that next week. The process of parametric amplification does that, or parametric, spontaneous parametric amplification, which is known as parametric down conversion.
Is this an entangled state?
It is. Well, that's an interesting question. When we talk about entanglement, we need to talk about subsystems. Okay? So what are the 2 subsystems? If we want to talk about bipartite entanglement, this is a single subsystem, which is a mode. It has an infinite number of levels, but so in the sense of the modes, there's no parts. There's no subsystem. Now I can think about the photons as the so when am I thinking about the systems as the particles or the waves? Okay, and I can think about this in terms of particle entanglement. We'll talk more about that later. However, it's a very subtle point about entanglement here. In your homework, problem 2 of problem set 1, we're going to talk about 2-mode squeeze states. And then there's clearly, this is related to entanglement between the 2 modes that are participating. But there's no, what's the tensor product structure here? You need a tensor product structure here. You need to talk about parts to talk about entanglement. And here there are no parts. This is a unary system that has one degree of freedom, which is the mode, the 1 mode. But it's a very subtle, interesting question. All right, I wanted to just maybe say one last thing before we have to quit today, which is to think about this from the point of view of the CV representation, which is just wave mechanics. So if I have a state of our single mode, we can think about it in the number basis as we have. We've expanded it in number states. But I can also think about it in the basis of the eigenstates of the quadrature. We call this thing in wave mechanics the wave function. Okay? Or I can think about it in the p quadratures. That's sometimes called the momentum space wave function. But here, it's the same thing. It's just that this is not the positional momentum of the photon, it's the quadrature of the oscillator of the field. Okay? So if I have a number state, I can ask what is the positions or the x quadrature representation of the number states. Okay? What is that? The number states, we remember, are the eigenstates of the harmonic oscillator. They're Hermite polynomials times Gaussians, right? So there's some normalization coefficient. There is a Hermite polynomial of order n times a Gaussian. Okay. So if I were to think, if we think about this in the usual simple harmonic oscillator, we imagine the ground state is a Gaussian, the first state is the first Hermite polynomial times the Gaussian, the second excited state, etc. Right? These are my U and X's. And the square of them represent the probability density for measuring those outcomes, X or P. Okay. Now, the squeeze state, written this way, for small values of the squeezing parameter, is approximately the ground state superposed with the first excited state, with that minus sign, okay? What that gives us is something, when I put the minus sign in here, which augments the middle and subtracts out the edges. And in fact, the squeeze state is also Gaussian. The ground state here, this is the ground state, is a Gaussian. This guy is also a Gaussian, but with a reduced width. We can see that in the following way. So I look at the position space representation of the squeezed vacuum state. It's that. Okay? But we know that the squeezing, when it acts on the position space representation, gives me an X eigenstate. It's got to be normalized properly, but okay, I'm not going to worry about that. So that means an S dagger on this is equal to S of minus R, which is e to the plus Rx. So this is the bra version of this. So this is e to the minus R times that. But with this form here, for the ground state, the Hermite polynomial is just the identity. It's a Gaussian. So this is equal to e to the minus plus 2r x squared over 2. So this is my wave function associated with the squeezed vacuum, which is equal to e to the minus x squared times 2 e to the minus 2r. Right? Just put it in the denominator. So what can you tell me about this Gaussian? Remember, the probability distribution is the square of the wave function, which is equal to this, without the normalization. I just squared that for 2. So now I ask you, what is the mean value of x and what is the variance of x for this Gaussian? The mean value is 0. This has the form of e to the minus x minus the average x squared over twice delta x squared. The mean x is 0, and delta x squared is what? 1/2 times e to the minus 2r, as we must have, right? Because it's 2 times x squared in the denominator. So the squeeze state is a Gaussian distribution of quadratures, but with a width that is reduced, and that width is reduced because of this interference. Okay. Now, I know I'm over by 5, but that's fine. I just want to, we're not quite at 5, but I want to say the last thing, which is, I want everyone, and not everyone was at the problem session on last Friday, I understand, I'm sorry, but to think about the implication of thinking about the parametric oscillation, the mechanical story of parametric oscillation, where in a parametric oscillator, what we're doing is we are modulating the curvature of this, we're making the stiffness of the spring go in and out at twice the natural resonance frequency. That's how we make squeeze states. And how that is a completely classical picture of what's going on in its relationship to this whole rigmarole about quantum interference. Anyway, let's get out of here. It's time for class for the next one. So I'll take questions outside.
Come on in, I'm sorry.
No, it's not. It's all that.